Okay, here I'm going to talk about power adaptive communication in W bands. This is the title of my PhD thesis at University of Otago. I did my PhD under the supervision of Dr. Aibo Zhang and Dr. Zhi Huang. A W band, usually known as a small network including a few or tens of tiny sensors. The sensors are attached to body parts or sometimes implanted in body tissues. The sensors usually are in charge of measuring a physiological or vital signal and then reporting their measurements to a gateway, sometimes in communication with other sensors or other wireless devices around. There are three important challenges when it comes to design a communication protocol for W bands. The first challenge is resource limitation, and that's because of the very tiny size of the sensors. For example, if a sensor is going to be implanted into body parts, it usually need to be designed very small, and that means the battery capacity would be very small. But on the other side, we expect a body sensor operate for 10 years, 20 years, and it is not acceptable to do a surgery just for recharging a battery or replacing a battery. Another challenge is interference. Well, you see, in a small size network as large as a human body, there might be a couple of sensors attached and communicate with each other, so that the network is very dense. Other than that, body networks are expected to operate in dense areas like hospitals, where many patients might be wearing such a wearable networks and walk around. So they may produce interference for each other. On the other side, body networks may coexist with some other networks in the area, for example, in indoor localization systems. So they may produce interference for each other. And that's very important to design a communication protocol that is interference aware. And the last but not the least challenge is communication reliability. Body sensors are usually in charge of measuring a physiological data, sometimes vital signals, and reporting these vital signals reliably is a very challenging and at the same time very important tasks for such networks. So the research question in my PhD was how to design a communication protocol to reduce energy consumption and interference range, but at the same time guarantee a communication reliability. And we know this designing such a communication protocol is very challenging because of a unique feature of body networks, and that's highly topology instability. So if I move to previous slide, you see here within a gate cycle, the location and generally the topology of the network is changing a couple of times within a fraction of time. So that shows how unstable the topology is. Well, we designed such a test bed. In this test bed, we have a transmitter at the wrist, a receiver at the gate. So we consider a star topology where all sensors at the body are connecting to the gateway. That's what's suggested in IEEE 802.15.4 and 0.15.6, which are the standards for body networks. So we chosen such as a test bed because, or such a scenario, because the wrist in combination with elbow and shoulder provides the most, or let's say, is actually the most mobile joint. I mean, the wrist is the most mobile joint in combination with elbow and shoulder, and that means the channel quality between the transmitter and the gateway in such a scenario would be subject to a high fluctuation. For our testbed, we use the telescope sensor modes, and this telescope sensor mode has a CC2420, so this is telescope, and it has CC2420 radio chip, and this radio chip provides a number of transmission power levels from level 1 to level 32. First of all, we did a measurement campaign and plotted this heat map, RSSI heat map, that shows the signal strengths around the body. And there were two observations from this measurement campaign. The first observation says that, or the first observation is that the channel quality, or let's say the signal strengths from transmitter to the gateway highly depends on the location of the transmitter around the body, or the relative location actually, or the location of the wrist relative to the chest or relative to the gateway. And the second observation is that a few centimeters change in the location of the transmitter doesn't change the channel, doesn't make a big change in the channel quality. So from the first observation, we concluded that if the sensor node knows its location, if the transmitter knows its location relative to the gateway, then it can properly adjust its transmit power. That means if the sensor node knows its location and knows the channel quality is good in that location, for example, the wrist is in front of the body, so the distance is a few centimeters, the line of sight pass is available between the transmitter and the receiver is available, then the sensor node can reduce its signal power, can choose a low transmit power and reliably deliver its packet, reduce its energy consumption, and potentially reduce its interference range. But if the sensor node is, or if the wrist is at the back of the body, then the line of sight pass between the sensor and the gateway is blocked by body part. The sensor node knows that because it knows its location, in case actually it knows its location, and it can adjust its transmission power, use a high transmit power level, and deliver its packet and achieve a high communication reliability. So knowing this in mind, we tried to design a inertial motion tracking system to help the sensor node to know its location. And for that, we need to equip this transmitter and the receiver with an inertial, with an accelerometer, a gyroscope, and a magnetometer. A 3-axis accelerometer, 3-axis gyroscope, and 3-axis magnetometer, then fuse all the information from these three sensors and then estimate the location of the transmitter. So we developed a system, something like this. Well, the only problem with this system is that for the sensor node here, if it wants to know its location, it needs to know the location of the elbow relative to shoulder. Otherwise, it cannot find its location relative to the chest. And that means for such an idea, we need an extra sensor to be attached at the elbow, which is not reasonable. I mean, it doesn't make sense. For reducing a battery usage, we use another extra sensor. So we developed another idea, and we, as I said in the previous slide here, I said that the second observation says a small change in the location of the sensor node doesn't make a big change in the channel quality usually. I mean, the channel quality is not subject to a big change because of a few centimeters movement. And that means if the sensor node can roughly estimate its location, it is enough for energy efficient, interference aware, reliable communication. So we decided to, instead of using an extra sensor at the elbow, we consider some biomechanical constraints on human body movements. Uh, and then we designed this system. Here you see I'm capturing a sensor in my fist, and this video here shows that how accurate we can, I mean the algorithm can estimate the relative location of the sensor node. I mean, it is enough if the sensor node knows it is in front of the body or it is in the back of the body. So such estimation is enough, and this video is showing that we can do using only a sensor node itself, and we can do that locally on the sensor node. This idea has been published in IEEE Transaction on Mobile Computing, and well, during the time I was doing this research, I found that there is a correlation between the channel fluctuation pattern, here shown by this RSSI, this plot. There is a correlation between this fluctuation pattern and the let's say the motion pattern of the sensor node. And the motion pattern can be measured by accelerometer, but here I've used a gyroscope, because accelerometer is subject to gravity. I mean, it measures to gravity, it's subject to outer forces like gravity, and it is noisy. You need to do some more processing, but angular velocity captured by or measured by gyroscope is quite smooth. You don't need to do much processing there. And then we developed a lightweight reinforcement learning algorithm. This reinforcement learning algorithm enables the sensor node to estimate the channel through locally measured angular velocity. For example, the sensor node knows if there is a packet to be transmitted, the sensor node first measures the angular velocity, the current angular velocity, the real-time angular velocity, and then among the transmit power levels it has, it randomly chooses one of them, transmit its packet. When it sends a packet, if the packet is delivered, the gateway replies with an ACK packet. The sensor node takes that ACK packet as a feedback and decides, okay, this is probably not a bad transmit power level. Then using a reward and penalty mechanism, it rewards the good power levels and penalize the bad power level. Here we defined a cost function. The cost function for a power level, let's say power level I, is proportional to a signal power level. So a higher transmit signal power level causes more cost to the sensor, and it is inversely proportional to the reliability of that power level, because we know that, for example, if the reliability of a channel is 0.5, then the transmitter on average needs to send a packet twice to make sure that the packet is delivered at the receiver. Well, this is actually a geometric random variable. So using this simple lightweight reinforcement learning algorithm, the sensor node can gradually learn at what is the best transmit power level at each range of angular velocity. For example, here gradually it finds that because the channel quality is low, maybe a high power level is good one, and if the range of the angular velocity is at this range, then it finds that maybe a low transmit power level is a good one, is a good choice. Here I made a video on how this system is gonna work. I made the simple version of this idea. We have a transmitter at the wrist, we have a receiver at the chest, and then the transmitter sends a packet. If the transmitted packet is sent using a low power level, then the blue LED is blinking at the gateway. But if the transmitted packet is sent using a high transmit power, then the red LED on the gateway is blinking. So I hope this is visible, and this shows how this idea works. Well, first we have a standing position, the channel is blocked, the transmitter is using a high transmit power, so we expect red LED blinking because it is high power level. And then I change the position to sitting. The channel quality is good, the distance is low, so gradually you see low power is adjusted and blue LED is blinking. And then I change from static postures to dynamic postures like walking. And we expect when the hand is in front of the body, blue LED starts blinking, and when my wrist is in the back of the body, the red LED blinks. Well, here maybe it's not visible. I have another video that shows, well, because of the learning nature of this algorithm, it sometimes takes a couple of seconds until the algorithm learns. But you see when I move my right hand, the back of the body, the red LED blinks, and when I move it in front of the body, then blue LED starts blinking. So this idea has been published. The initial idea has been published in conference paper, PICOM, and then the extended idea has been published at in ACM Transactional Embedded Computing System. And finally, we developed another idea using, well, here in this idea, we try to capture, or let's say, to answer some other questions other than the questions we could address in the previous ideas. And the question here is that if the channel is bad, if the channel quality is bad, for how long the channel remains in that bad state? And if the channel is in good state, for how long, for how many time slots the channel remains in that good state? And we try to answer this question by employing an improved version of Gilbert's Elliott Markov chain model. If the sensor node can answer such a question, then for a single packet transmission, it can decide if the channel is bad. Maybe it's better to postpone the transmission within a deadline and then transmit the packet when the channel becomes good. I mean, it can predict the channel fluctuation. We then found this optimal transmission time using dynamic programming. This idea, the initial idea, has been published in LCN conference, and the extended version of the idea has been submitted to IEEE Transactional Mobile Computing System. Well, in parallel with my PhD, I did some other works, mainly in collaboration with physiotherapy department. This is the idea that was supposed to be part of a bigger project for smart soccer shoes, and the smart shoes, let's say, for a sport, because it can capture the way the players are, for example, kicking the ball, and there are lots of information we can extract from this. The second idea, or another actually idea, is capturing or monitoring a spinal curve during different physical activities. Well, there are lots of applications for this. For example, it can detect bad posture, and it can be used for monitoring the treatment of a disease which is called, I think, scoliosis, if I'm not mistaken, which is a disease regarding some deviation in the spinal curve. And then we developed another idea for tracking physical activity and detecting what kind of physical activity and what kind of body posture the subject has using two sensors. And well, this is the first idea. Then we found that we can even use one sensor. However, we may lose some accuracy. Well, this was supposed to be part of a project for monitoring elderly people, physical activity in elderly people, and see how promotional programs have made them whether more activated or not, and also measure the physical activity among the school children to see the correlation between obesity and their physical activity level. Thanks for your time and attention.